Hi there. In this video, I'll be showing you how to simulate the operational amplifier using Multisim for the inverting and non-inverting. So over here, this is the IC, right, of the LM741CN. Okay, the dimensions is like about 1 cm by 1 cm. Okay, so the symbol representation for the op-amp is this, right? So LM741CN, there are actually different types of the version for these op-amps. Okay, but in the Multisim, we'll be just using the 741, right? Because I've realized that the LM741CN has some issues on the datasheets internally in the Multisim. So therefore, I've decided to go with just 741. Okay. So now, these are the pin configurations for the op-amp. So 1, 5, and 8 are the pins that are not going to be used. And then as you can see, pin 2 is for the inverting input, pin 3 is for the non-inverting input, pin 4 is the negative voltage, pin 7 is the positive voltage, and pin 6 is the output. Okay, so usually pin 2s and 3s are connected to the function generator depending on whether it's an inverting or non-inverting circuit. And then pin 6 here, this will be connected to your oscilloscope. And pin 7 and pin 4 is the VCCs, right, the voltages, to actually turn on the IC. All right, now as you can see, this is the inverting operational amplifier circuit. So right here, as you can see, right, the input is going to be the function G going into the resistor R1 and then going into the negative pin, which is the pin 2, right, since we are doing the inverting side. Now pin 3 is going to be grounded, and then from the negative input pin 2 here, there's going to be another resistor R2 connected to the output pin 6. Now this is the formula being derived where V out equals to negative R2 over R1 multiplied by V in. Now you realize the negative, right? The reason for the negative is because is that this is an inverting circuit, so directly there'll be a negative at the equation. Okay, later on you will have a view of it when we are going to be measuring the output side and the input side in the Multisim, right? So right now, so what happens then is that since we are looking for gain, so gain is actually voltage output over voltage input, right? So we bring the V in to the other, to the bottom of the VO, all right, and we rewrite the equation to be this. So therefore, to find the gain, we are going to be taking the resistance R2 divided by R1 and negative, and we will get our gain value in negative for the inverting operational amplifiers. Now for the non-inverting, what happens is that the connections of your resistance, right, since it was connected to pin 2, now it's going to be connected to pin 3. Okay, pin 3, which is going to be the non-inverting side. Sorry, it still remains, just that your input now is going to be actually connected to pin 3. Alright, my mistake. Pin 3 now is going to be connected to the input, which is the function generator. Pin 2 remains there, just that now instead of it being connected to the input, it's going to be grounded. Alright, and same connection as R1 and R2 as the inverting side. And now what happens is that the output equals to 1 plus R2 over R1 multiplied by the input voltage. Okay, so what happens, we're going to rearrange the V in to be brought over, and we will get again our gain for the non-inverting circuit, right? So we'll get 1 plus R2 over R1. Now as you can see, right, over here you can't really have a negative value. Why? It's because it's a non-inverting, meaning that it either amplifies the circuit or de-amplifies. Alright, so now what are the components that we're going to be using for our simulation? So one is going to be the 741 IC. Okay, 2 is that we're going to have 2 resistors. It can be either 1 kilo ohm or 2 kilo ohm, depending on how your R1 and R2 are going to be placed. Sorry, not placed, the scenario. Okay, scenario here is that we're going to be doing 3 different scenarios, right? Where R1 is more than R2, or R1 is lesser than R2, or R1 equals to R2. Okay, and then power supply here is mainly for the pin 4 and pin 7, and grounds, right? Oscilloscope is to display the output, a function generator for the input into the IC 741. So we need to set the frequency to be 50 Hertz, and then we can set the amplitude to be 0.5 volts. Now, when the amplitude is 0.5, so our peak-to-peak value is going to be 1 volt, right? So these are the scenarios that I was talking about. So R1 bigger than R2, R1 smaller than R2, R1 equal to R2. So these are the resistance value that we're going to be setting for our multisim, right? And over here is going to be the tolerance formula. Okay, this is to calculate between the measured and the calculated values that we obtain later in the multisim, right? So over here there are I've already pre-done the values actually, just to show you on how it's going to look like. So let me zoom it out a little bit, right? So now let's go actually into building the circuit in multisim, right? So as you remember, right, Control W is the shortcut to obtain. Now since we are looking for the ICs, so let's go into looking for the ICs. Okay, so what are you going to be looking for? We're going to be looking for basics, right? And then we're going to be looking for okay, sorry, not basics. Let's go to the analog, right? So there you go. So you can see there is like few types, but we're going to go for op-amp. And as I said right previously, we are not going to be using the exactly LM741, right? Okay, I can just type it here. Yeah, we are not going to be using exactly this one. Okay, what we're going to be using is this one, right? So click OK, drop it, and then now we need resistors. So resistors, we need 1K, and probably, yeah, just click it and we can change the value later. Okay, then what else do we need? Yeah, we need a oscilloscope, right? So this is for our output, and then we need a function generator. So here we go, right? And what else do we need? We need a supply, power supplies, right? For the pin 7 and pin 4. So Control W, and we go into sources, right? Power sources. Okay, so for this, right, I'm going to let you know something is that we can't really use the same VCCs, right? Because what happens is that, let me show you. So for now, let me just change this to 12 volts. Okay. So we need two different VCCs, right? One positive, one negative. So what you see, what happens is that if I put a negative sign for this one, right, what happens is that it will also appear here. Okay, it's because they are represented by the same label, right? VCC. So what happens right now is that instead of using this same one, right, I'm actually going to call a different voltage source. This is VDD, right? So for this one, I can just double click, change it to 12. So you see, it's fine, right? Then yeah, we need ground, right? Don't forget that. So get ground. Right. Is there anything else do we need? Let's check our list. Two resistors, supply, ground, oscilloscope. Yep, I think we are there. So now let's go to this image here. So they say input function G, and then to negative pin. So pin 2, and then pin 3 is going to be grounded, pin 4 is the negative supply. Okay, so let's go here. Yeah, so we're going to rotate this, right? And this is our pin 7 for our positive supply. Okay, then sorry, pin 2 is inverting, so yeah. So you're going to connect this to here, and okay, so we have two channels on this oscilloscope. So what is going to happen is that A is going to be our input channel, B is going to be our output channel. So connect this to here, okay, and yeah, I'm going to need a few more grounds. Okay, the negative side of the oscilloscope, right, for this, yeah, it's going to be connected to, okay, just let me zoom in to show you. So yeah, input, output. So you can see that the positive side will be connected to the output to display, and the negative side will be grounded. Okay, now since this is going to be our input, right? So now, okay, so connect it to here, and the COM is going to be grounded. All right, now we want to display the input, right, so that we can show a comparison. Okay, sorry. So now, okay, let me change as well. Since we are doing the first scenario is R1 bigger than R2, which means that R1 is going to be 2 kilo ohms. So we need to change this to 2 kilo ohms. Right. Now, everything is set, but now we need to configure our function G, right? So go to your function G, change this to 50 Hertz, right? Then now, amplitude. Our amplitude is 0.5 volts. Now, it's not peak to peak, but we need to change it to MV peak, right? Yeah, MV peak, okay? 0.5 millivolt peak to peak. Okay, later on you'll see what exactly happens. Yeah, correct. So then, I think we are connected. Oh yes, another one more ground here, right? Remember, don't forget that. Okay, pin 1, 5 is not being used, and yep. So let's run this. Okay, so we're gonna reverse this, right? Now, since our voltage, right, is just 0.5 volts, so what we're gonna do is make sure we reduce our input channel. Okay, I think I made a mistake over here. This is supposed to be V peak. Ah, 0.5 and then peak. Yeah, sorry about the mistake. Yeah, now we got everything. There we go. Okay. So it's a bit difficult to observe, right, once we stop it, and then yeah, we can't really know which is which. So what I would suggest is that we change this color, right? Segment color, we can just change it to blue. Okay, so now that means the blue represents your input and the red represents your output, right? So there we go. Okay, let me now zoom this in a little bit. Okay, let's stop it. So I'll go back to the beginning. So as you can see, right, it's consistent, right? Now, how do we actually view the oscilloscope over here, right? So now, as you can see, right, channel A is our input and the scale is 500 millivolts per division. So meaning that this is one box represent is 0.5 volts. So it's exactly almost 0.5 volts, right? This particular input wave. And your output is represented. Okay, let me change this also to 500, right? So we'll have the same particular, how to say, scale. Okay, now the scale for time base for one box is 10 milliseconds. So since one wavelength will be your period, right? So you plus 10 milliseconds plus 10 milliseconds, you get 20 milliseconds. 1 divided by 20 milliseconds, you get 50 hertz, right? So it is correct, right? 50 hertz for both input and output. Okay, so now let me show you a trick to how to get exactly in the middle of the wave, right? So that you can actually obtain the highest voltage peak on the positive or the negative side, right? So you can use this particular how to say, rulers, I would say, right? So you can click on it and you can define, right, two maximum peaks or minimum peaks. So right now I'm actually on the input side, as you can see, right? Once I move, you see it's still on the input side. It's going only on the input, the blue one. Even though this is in red, it's not actually going on the output side. It's also still on the input side. It's actually to create like a difference calculator between for the inputs on the maximum value and the minimum value. So right now let me push this back to here. Okay, so you can click and then you see you can select, right click, and then you can select to go to the next Y minimum, right? So it's over here. Now for this one also I can just click, left click and then right click, and then say that I want to go to the next maximum Y point. So you see, now this is the maximum Y point and this is the minimum Y point. So you can see over here, right, your maximum point, your input is 499,254 millivolts. Now your negative, right, how to say, input is negative 499,254 millivolts, right? Now I want to click. So if you want to see the how to say, the rulers to be on the output side, just click on the red line. So you see, you'll straight away switch. So now you switch already. Okay, I need to get the positive value, so it's going to be the T2. So what I'm going to do is that I'll push it back to the previous one. Okay, yeah, and then again back. Okay, I got the wrong maximum. Yeah, so you can see that. Okay, sorry, I think I should go the other way around. This should be at the bottom, and yeah, this should be in the maximum. Yeah, okay, so then you see 251.24. Alright, so these are the values that you obtained for your output and your input, right? So right now what happens is that, since, as you can observe, right, you are taking a positive value, since your input, right, if your input is positive, okay, we are in this one, so your input, right, yeah, so since your input is positive over here and your negative, what is it going to be, right? Yeah, so you see, since your, okay, let me get this one better. Okay, now you see, since your input over here, right, so this is T1, right, the ruler is called the T1, so you can see T1. So over here, so your input is 499.245. Now the negative is negative 248, right? So you can actually just fill it up, right? So you can say that it is actually 248. So I actually got 25, so it's anything is okay, right? So you can say it's 248, right? So now what happens is that you're definitely going to get a change of the gain, right? So the measured gain now will be changing, right? So you're gonna get you're gonna take the output, so it's gonna be 0.248, you divide by 0.5, so there you go, you get your gain to be 0.496, right? So you can see on the calculated gain, you're just taking the resistance value 1 divided by 2 and you get negative 0.5, right? So error here is the tolerance calculation. You can perform it yourself, right? You already have the formula here. Okay, so you can calculate the error formula based on the calculator and the measured here. So the next thing for the inverting you can perform is that you can see R1 more than R2 and R1 equal to R2, right? So I'm not going to be performing. You can just change the resistance value and you can get your values of your graph, right, on how I did just now for the inverting side. So these are how I've done the calculations as well. Okay, so I've changed the values here. Later on you can have a look at that. Alright, so if let's say, now let me give you another thing. Remember previously when we were doing the potentiometer lab, right? So whenever it is like this, 499.739, so as we try to change it to volts, we'll observe whether this is higher than 5. If it's higher, yeah, if it's higher than 5, yeah, then we have just directly convert to 0.5 volts, right? So observe how exactly the graph displays the value and you can just bring in the value, right? So for example, like this, 497.698. So what's going to happen is that the value is going to be 0.498 volts, right? All right, now let's go into the non-inverting side. So non-inverting side basically is the same, almost the same configuration, just that we're going to change the pin, right? The pin, instead of the input going into this negative pin, it's going to go into the positive pin, right? So now let's we'll just copy this, right? And then we'll just create okay. Now let's just disconnect this. Sorry, not that. We'll disconnect this. Okay. Move this here. Disconnect that. Yep. Then I think we're done. Right? Pin 3. Right? Connected to the input, which is the positive, right? Yeah, non-inverting. So that's about it. and this pin is going to be grounding and connected to the resistor, and yeah, I think we're done. So how simple was that on doing the simulation, right? But in the practical side, it's going to be a little bit hectic, because yeah, sometimes the pins might get broken when the student try to adjust it. Now what we're going to do is just run, and we can directly see the value. So in the calculated side, now see the calculated side. So as I've just continued the resistor value R1 to be 2 and 1, so it is seen that I will actually obtain a 0.75 volts and the gain is 1.5, right? So that means it's an amplified scenario, right? So right now let's run this. Okay, reverse it so that we can see a very nice one. Okay, and we can stop it already actually. So there you go. So you see, the blue is our input and the red is our output, right? So now just move this, yeah, to here. So as you can see, okay, let me move it to the next maximum. So now 0.5, okay, so over here, see the T2, T2, so 499.245. Okay, so you can actually adjust your input here, right? So let's adjust our input to be 0.499 volts, right? And what do we get for our output? Our output is actually 750.4. So you see, if it's 4, that means we can neglect and we can just take it as 0.75, right? So as we have it here. Now the gain measured, so it's going to be this divided by this. So what are we going to get? So let's see, 0.75 divided by 0.499, right? 1.503. Okay, so that is my gain. So yeah, so you can try out for the remaining scenarios for both the inverting, right, where R1 is more lesser than R2's value and R1 is equivalent to the value, right? Same goes for the non-inverting. Try out the two scenarios and yeah, give it a try, and check, also do the tolerance calculation to check on how exactly the tolerance is affected, right, for this particular operational amplifier simulations. Okay, thank you.